Hello again. Thanks for joining us on Space Nuts. I'm your host, Andrew Dunkley. This is episode 355, and as we tend to do every fifth episode, we dedicate it all to audience questions, which we'll be doing today. We'll be looking at the expansion of the universe, what it's like to actually stand on another planet. How will your eyes work? Will you see what is actually there? Will they work properly? We're going to talk about causation. We're going to one really fascinating question is, does a planet need a moon to bear life? And a few other things like tumbling in space, what happens there, and a bunch of other stuff, all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to answer all is Professor Fred Watson, astronomer at large. Hello, Fred.
Good day. Is that the correct term? Good day.
Depends if you're talking English or Australian.
Good day, Andrew.
G'day.
Oh, so
It's g'day. Soft on the G.
yeah, soft on the G, that's right.
Yeah, it's amazing though when you're overseas, particularly Canada and the US, how many people try to say it to you.
Because they know you're an Aussie.
Please don't.
Well, I do too. Good day.
No, it's just a thing, isn't it? We're known for saying it. So
Yes, that's right.
and we do. It's just a part of our natural vernacular, isn't it?
Exactly so.
Yeah.
Exactly.
Anyway, we've got a heck of a lot to cover. Did you have some homework from last week that you wanted to deal with?
I did.
Oh, okay. Well, let's knock that over first.
Do you want to hear that?
Sure.
Okay. We had a question from, I think it was, where are we? Yes, it was Rusty.
Well, he's got another one for us. This,
Was he?
yeah.
And he was talking about, I think he'd read about a white dwarf star that was 10 billion years old.
Yeah.
But that contradicts all. The problem with white dwarf stars is that they are the end product of normal stars like the sun. So you only get a white dwarf when the star runs out of its energy, and it is by then about 10 billion years old. So the star is about 10 billion years old.
Yeah.
But the universe is only 13 billion years old. That's right. So if you've got a white dwarf that's 10 billion years old, and I think that was the number, then you can't have a star that's gone through its life and then formed a white dwarf, and that was 10 billion years ago, because that makes 20 billion years, and the universe isn't that old.
Yeah.
And I think that it may well be that what Rusty read, I don't know because I'm not in Rusty's head, but what he read was that maybe the age of the star is 10 billion years before it forms the white dwarf.
Maybe. That would make more sense.
The record breaker for a white dwarf, in other words, a star that has become a white dwarf, at the end of its long life, it's turned into a white dwarf. That record is an object whose name I had in front of me a minute ago. I wonder if I can find it again, because it's not the kind of name that you come across every day.
Okay.
It is called LSPM J0207 plus 3331.
Right.
That's the oldest white dwarf star, and it is thought to be 3 billion years old. So that means, if its progenitor star did last 10 billion years, then it turned into a white dwarf, having shed its outer envelope. Then you've got 3 billion years, and it still means it's within the age of the universe. So
at that age, it whinges about everything, blames the government for everything, and thinks young people have no idea.
Yeah, just like me.
Young stars have no idea today.
I don't do any of those things.
All right. Was there another one?
Yes, there was, about what you would see inside a black hole, and that's...
Oh, if you were trying to look out.
Yes, but you wouldn't be in the black hole, because the black hole is a singularity, and once you're in there, you've had it. But you would be within the event horizon. And it turns out that the gravitational distortion is so much that the singularity itself, which is black, fills your entire field of view because of the gravitational distortion. So it's dark.
You'd see
Dark
nothing.
inside the event horizon, that's right.
Okay. Very good. All right. I like this homework situation.
Well, it means you get a better answer than the one that I pull off the top of my head, which is the usual scenario.
You're very tough on yourself, Fred.
Based, of course, on nearly 60 years of astronomical experience, but that's all right.
Yes, as against 4 billion years of astronomical.
Which is coming next.
Yes. All right, let's get stuck into our questions. And the very first one comes from, in fact, these first two are related, but they're different questions. The first one comes from Gary.
Hi, guys. It's Gary from Sale in Manchester in England. Obviously, love the podcast. Love this. It's one of my favourites. I listen to it all week and I really do look forward to listening to it. But I do have a question, and I was hoping you may help, or maybe it's just a theory or just a bit of a moment of madness. So the universe is or the edge of the universe is expanding at faster than the speed of light. What I was wondering, could this be caused by the fact that space itself between here and that point actually is a vacuum, obviously, but is there a density to it which is created by dark matter? And obviously, as there isn't anything to which is therefore restricting light or anything to travel beyond the speed of light. But at the end of the universe, there's nothing there restricting it. No dark matter or energy or anything, and is space therefore having the ability to expand? I was also wondering if that could be influenced by heat. So at the end of the universe, I would assume that it's on the premise of the universe, it's free or a bit more, below to the point where there is no measurement on heat, and therefore does that give it the ability to expand? And as soon as you put anything above -273 into the equation, does that therefore force it to be some form of restriction on the ability? Therefore, dark matter is influenced by something else. Anyway, bit bonkers, but hopefully you can give something about and let us know what you think.
Dear. Okay, thank you, Gary. Bit bonkers. He thinks his question's a bit bonkers. It's a big one. It's a big question.
It's got lots to it. But lovely to hear that that Northern England, the flat vowels that I've had all my life. And I'm just going to do a quick aside, harking back to something that we were talking about a few minutes ago. The Australian way is g'day.
Yep.
Where I grew up in Bradford in the north of England, the greeting was, now then.
Oh, really?
Now then.
I thought you were going to say "ew."
No,
that's Liverpool, isn't it?
No. Well, it's "eup's" different. That's
"Eup."
That's an alert signal. "Eup." Whereas hello translates to now then,
really?
Which is now then. Yeah, and that was it. Usually that's all you got, now then.
Wow.
and I'm sure Gary, listening to this from Sale in Manchester, I think it's probably very similar in Manchester. It is across the border, of course, the Lancashire-Yorkshire border. But yeah, now then. So I should use that when we start the show, shouldn't I?
You should.
Yeah.
Oh,
so
okay.
The trouble is, people where I grew up, they don't say much, and quite often now then is all you got. So let's move on to the question.
Indeed.
About the edge of the universe. Well, yeah, so the horizon that really stops us from seeing any further into the universe is the cosmic microwave background radiation. And in a sense, that tallies with what Gary's saying, because that horizon is actually receding from us at the speed of light. It's all the time, it is moving away from us at the speed of light, which sounds crazy. But it's currently 13.8 billion light years away in the reference frame that we're that we can understand. There is a point beyond which we cannot see, and it is flooded with radiation. Now, that radiation permeates the whole universe, and probably the universe beyond the horizon as well, because it's the same thing. It's a radiation that comes from the Big Bang, that wherever you are in the universe, you're looking back so far in time that you're seeing that sphere of radiation surrounding you. You're in a bubble. And I call the cosmic microwave background radiation the cosmic wallpaper, because it's behind everything that we can see. All the galaxies, stars, planets, everything is in front of that. So that's a horizon. And the idea of, because it's a radiation, it's got a temperature, and the temperature is 2.7 degrees above absolute zero. That's the temperature of space.
Wow.
And it's the same everywhere. And so, Gary's point, our idea about the warm universe being, or the outer, the sort of beyond the horizon being colder than what we are, doesn't really hold up, because in fact beyond that horizon it's hotter than what we are, because you're looking back at the Big Bang itself.
Yeah.
But the temperature in our area is 2.7 degrees above absolute zero. So I think there is the pressure that Gary speaks of is essentially the radiation, the dark energy that we don't really know too much about. Dark matter behaves like normal matter does as far as gravity is concerned, and it pulls back on the acceleration of the universe. It tries to slow it down. But the dark energy, the energy of space itself, that springiness of space, is fighting against that and wins easily, because it's about 75% of the mass energy budget of the universe. So some interesting ideas there, Gary, and I'm glad you sent that to us, because you formulated things in a different way. But the bottom line is, I think we're still baffled about what dark energy and dark matter are.
Yeah.
And we still have a universe whose edge we've never seen, and which may not have any kind of limit. It may be infinite, and we don't know the answer to that.
Yeah. If there is an edge and it's moving out at the speed of light, if we knew the actual size of the universe, it would be just unthinkable as to how much bigger it's getting every split second.
Yeah. In fact, that's sort of that. You can say that about the cosmic microwave background radiation, the way that is receding from us at the speed of light, and you can't see anything beyond that. But if you were in a different part of the universe, you'd still see it receding from us at the speed of light, and it'd look as though it's 13.8 billion light years away. But because the universe is so big, we really don't know what's beyond it and how far on it goes.
No, it's a big question. And thank you, Gary, for sending it in to us, which leads to another question from Rod. On large scales, the universe is expanding by increasing the amount of space where whatever force is causing the universe to expand, that force is greater than gravity. I hope that makes sense. However, if space itself is expanding and time is bound up with space to be space-time, does this mean that on those large cosmic scales, time is also being created along with space? In other words, the very fabric of space is being created. Or is the existing fabric of space being stretched? And what does that mean for time, or the time part of space that is being stretched? Would time run slower in that stretched space? Thank you very much, Rod. And thanks for signing up. He's become a patron. We really appreciate that kind of support. Right. So thank you very much indeed, Rod. And that too is a very interesting way of thinking about the expansion of the universe.
Yeah, so time is bound up with space in this thing we call space-time. But what's interesting is that to talk about an expansion, you're talking about a rate, something happening at a rate, and a rate always tells you that time is in the denominator. So it's something divided by time gives you a rate, and so time's kind of in there twice, which is a bit odd. Maybe it cancels out. But we think in cosmology, we do think more in terms of the expansion of space itself. Rod's right. I didn't pick up where the Rod's from, actually.
I didn't say.
He didn't tell us.
No. I don't think it came up on the email.
Maybe not. Not that makes any difference. The answer to the question could be different if you're in Lancashire, though. The idea is that the universe. Yes. What I was going to say was, if you think about rest frames, that's what you've got to get your head around in terms of the relativistic ideas. So we are in a rest frame that is kind of sitting there quite at peace with the universe, well, most of it, and sort of watching all this motion take place. But if you think about the fact that when you look back in time, which we are doing with our telescopes, then you're looking at a different rest frame. And even if time was behaving in the same way, then it would look slightly different to us. And we see that effect in the way galaxies evolve and the way they behave. You have to put in a sort of relativistic correction because of the different the different reference frame that we're in. And I'm kind of making a bit of a hash of this because it's quite a complicated question. But the bottom line is, it's probably easiest to think in terms of just space when we think of the expansion of the universe. Time will change, but by amounts less than what you might think in terms of, the time dilation, the gravitational time dilation, things of that sort. I suppose the best instance of it is when you look at, and I think this is going the right way. When you look at the steps in the earliest phase of the universe's life, we talk about all these things happening, but they happen within 10 to the minus 33 of a second or something like that. So everything is really squashed up. And I think should check this, but probably part of that is because of the relativistic effects.
Okay. I hope Rod understood what you just said because
I wish I did.
I completely bamboozled. Dear.
There you go. Well, can we tune in next week, listeners? You'll be baffled again.
Yeah, that's part of the job. Thank you, Rod. I appreciate it, and we appreciate you becoming a patron. So that's terrific. Next question.
Cancel his membership after that.
Maybe. Next question comes from Janis.
Hello, Space Nuts. I'm Jens from Sweden. I think the most evocative data from space exploration are the images and videos from the landings on foreign planets and moons, like Venera on Venus, the Mars rovers, and Huygens on Titan. They make me imagine that I stand there at these places and look at the surroundings. But what would I actually be able to see in those places? Venus has a very thick atmosphere that probably blocks much light. Mars is further from the Sun than Earth, and Titan is even further. How bright would an unaided eye perceive these places to be? Would it be too dark to see anything? We can assume that I stand in each of these places at the equator at noon. How well would I see? Thank you for a good show.
Thank you, Janis. It's an interesting question, and eyes come up in astronomy and space science a lot because when you're off the planet, it's one of the things that's at risk. Eyesight or your eyes in general physically can be affected by zero gravity in orbit, and there have been documented problems with that. And I imagine if you're on another planet, and the gravity's different, you'd face the same perils. But how would your eyes work properly in a different environment?
Yeah, so putting that to one side slightly, you're absolutely right. Gravity, we know from what's happened on the International Space Station that zero gravity actually affects eyesight. And all the objects that Janis mentioned, except Venus, has different gravitational pull from ours. So, but that's the kind of thing that is a long-term effect. It's something that, affects your eyesight over time. It doesn't affect the perception at the time because your eyes still work pretty well in those conditions. But he's right that all of these worlds would probably be dimmer than what we see on a bright sunny day here on Earth. Certainly Venus has these thick clouds. Venus isn't somewhere you want to hang around anyway.
No.
But the Venera spacecraft all used visible light as their, to take the images that they took, and you can see details on the surface pretty well as you would with a camera here on Earth. Mars, again, further away from the sun, clear skies, but further away from the sun, so the radiation's lower. And Titan, with the Huygens probe landing on Titan, further away still, and pretty gloomy, really. But having said all that, if you were transported there I'm pretty sure that you would see pretty clearly during the day. And the reason I say that is our eye has an incredible range of sensitivity.
Yeah.
It can cope with the brightness of a summer day. It can cope with starlight, which is millions of times fainter. And our eye is so adaptable to these different light levels that you would still see things pretty well during the day on those worlds. I was reminded of this actually a couple of months ago, nearly, when I was watching the solar eclipse, the total eclipse of the sun on the 20th of April, and that you're seeing more and more of the sun's disk being covered by the moon as it progresses. It's about an hour and a half for the moon to cover the entire disk of the sun, and during that period, you really do not notice the drop in illumination. Towards the end, you start seeing a kind of greyness about the landscape. It's different in colour, but your eye is kind of keeping up with the changes in brightness. And you know that, 95% of the sun's disk is obscured, and you can still see perfectly well around your surroundings. So the eye is really astonishing in the way it adapts to different environments. And I'm sure it would on all these worlds.
Yeah. I think you told me not so long ago that the eye is so powerful that it could see as little as one photon.
There has been experiments, yes. Yeah. We did talk about it a year or so ago, that some physiology experiment demonstrated that the eye responded to one photon, which is incredible.
Amazing. Yeah.
It is incredible. That's right. I've forgotten that, Andrew. Thank you for reminding me about that.
That's all right. That's what I'm here for.
Yes.
Occasionally useful. Thank you, Giannis. Really love that question. It's a good one. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Our sponsor NordVPN is a great option if you're looking for a virtual private network to protect your personal information, your bank accounts, anything you do online, basically. And it's as simple as signing up. And of course, as a Space Nuts listener, you can sign up with extra benefits. Just go to nordvpn.com/spacenuts and get the deal. Now, first and foremost, you get a 30-day money-back guarantee. They back their gear, and they are certainly one of the best, if not the best, in the business. And it works on all the platforms, major platforms, Windows, Apple devices, Android devices, smart TVs, you name it. And they are global. So it doesn't matter where you are in the world, you'll be able to access a NordVPN server. They're fast, they're efficient, they don't break down. You can secure 6 devices with a single account. It is really a good idea, especially if you travel, to have a virtual private network protecting your mobile phone or your tablet. I've got mine on all the time. So whenever I'm online outside the house, I have NordVPN on my mobile phone and my tablet, and I strongly advise you to do the same. And you can get a deal as a Space Nuts listener, as I said, nordvpn.com/spacenuts. That'll take you to a page where there's some information about the services they offer. Then you can click on Get the Deal, and you can see what option suits you. You might not need all the products that they offer, so you can sign up for a lesser deal. But if you want all the bells and whistles, that's available too. Now, the longer you sign up for, the cheaper it gets. And another benefit as a Space Nuts listener is you get 4 extra months at no cost. So check it out today, nordvpn.com/spacenuts, and enjoy the benefits of a virtual private network.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, we'll just sort of continue on because we've got so many questions to get through. And we mentioned Rusty earlier. Rusty sends in questions semi-regularly. And again, throwing us a curveball. Here's Rusty.
Hey, Fred and Andrew. It's Rusty in Donnybrook, looking at a perfectly clear night sky here. And I've been noticing that the plane of the ecliptic seems to intercept due east and west. about midway between summer solstice and the autumnal equinox here. And probably the reverse happens between the vernal equinox, the spring equinox, and the summer solstice again. So I'm just wondering if you could enlighten us a bit more on that. And, still haven't been able to work out why Fred hasn't got a knighthood for being the most influential practical astronomer alive today. And Andrew probably should get some sort of award for creating this podcast about the best podcast ever. Cheers. See you guys.
Thanks, Rusty. Oh, he's so nice. The plane of the ecliptic.
Ecliptic, yeah.
Ecliptic, yeah. So, that's what I said. Please explain.
So Rusty's commenting on when it lies, I think he's commenting on when it lies due east-west.
Yeah.
Which is when it crosses the equator. So the equator of the sky, which is just an extension of Earth's equator out into space, that crosses the horizon anywhere on Earth, due east and due west, because it's the equator. So the celestial equator, the equator of the sky, goes directly over your head when you're on the equator of the Earth, because, as I said, it's just an extension of the Earth's equator into space. Now, the ecliptic, the path which the sun takes throughout the year, is inclined at that to the equator at 23.5 degrees. So as the year progresses, the ecliptic is going to cross the east and west point. In fact, it says the day progresses because it happens every 24 hours. You'll get this point where the ecliptic crosses the equator, which rejoices in the name of the ascending and descending nodes of the ecliptic. Node is a word that means it's short for no displacement, and so what that means is it's not displaced from the equator at those points. It's crossing them. Yeah. So if you've got, I can't remember the details of what Rusty's question was, but you can kind of work it all out from there, because if you have this, if you imagine sunset and you imagine it's at the equinoxes, then the sun is actually crossing the equator. So the sun sets due west. It means that on the other side of the sky, the ecliptic is also crossing due east, and so and vice versa. So it's just a question of being able to imagine how the tilt of the ecliptic works its way around the sky. I'd suggest one of the best ways to visualize all this and get your head around it is to use a planisphere. The little star wheels that you've got.
Oh, yeah.
Because they usually have the ecliptic marked on them, and they certainly have the equator marked on them. Well, if it's a good one, it does. And so you can see, you can see what times of year you're going to have it crossing the horizon. No matter whether it's crossing whether it's the ascending or descending node or not, you can see when the ecliptic crosses the horizon.
Is there a visual effect when you witness this, or is it just,
it's just
like every other day?
It's just geometry, yeah. It's just like every other day.
Yeah.
You wouldn't notice unless you were watching carefully what the sun was doing throughout the year. Okay. It's why, what we're talking about is why the sun's rising and setting points shift along the horizon. So, in our summertime, the sun shifts towards the north on the horizon. In our wintertime, it shifts towards the south.
Yes, some ancient civilizations have built calendars on that basis, haven't they? With put rocks on the hills to pinpoint where the sun is at certain times of the year. Very good.
They have.
All right, thank you, Rusty. Another headache-creating question now. This is a big one. This one's been doing the rounds on our social media platforms, and a lot of people chatting about this. It is Matt, and he's asking about causation.
Hi, Frank and Andrew. This is Matthew from Adelaide, South Australia. I'd like to ask the question is, what is the connection between the speed of light and causation? I've been thinking about this now for a couple of days, and it's been doing my head in. So I'm hoping you guys can help me out. Thank you.
Okay, thanks, Matt. Take it away, Frank.
Okay, Martin. Well, in answer to your question, there's a technical term that I want to use that I'm going to have to look up. Yeah.
Oh, okay. It's another easy one.
Yes. Look, the bottom line, and the best way to think of this is to think about diagrams. And that's what I was just looking for there, and I'm trying to find it. So what's the speed of light have to do with causation? And it's all about the fact that the speed of light is the speed of information. So if you think of an event taking place within our range of visibility, let me put it that way.
Yeah.
So supposing let's say something happens to the sun. Now, if something happened to the sun now, we wouldn't know about it for 8 minutes because of the length of time it takes the light to get to us.
Yeah.
And so if you put the sun further away than 8 light minutes, I'm not going to be able to explain this very well without looking at a diagram. There are regions where you can put the sun and it can't talk to us. And so there's no causality. It's to do with it's basically to do with space and time. And the diagram I'm thinking of is a plot which has time going on one axis, usually the vertical axis, and space going the horizontal axis. If you've got a region within which you can see, which is getting bigger as you go up the time axis. So you've got something, you can think of it as a line at 45 degrees. And everything on one side of that line can have a causal influence on you because it's within the time that light will get to travel to you. But everything outside it won't because it's not connected to you by the speed of light. I really am explaining this very, very badly, Andrew. But it's
I wouldn't know.
It's worth going to the web just to have a look. The reason why I was looking was because these diagrams have a name, and that's what's eluded me at the moment. But before the end of the show, I'll find it and we'll work out what it's called.
Okay.
Probably called a space-time diagram. That would be the easiest way.
Possibly is.
Yeah.
Okay, so that's it's another confusing one, I suppose, from my standpoint. But yeah, it's certainly got people talking about it online.
Yeah, I think it's called a Minkowski diagram, named after Minkowski, who's the mathematician who proposed it. But we will see. Yes, that's it. That's it.
That is it. All right.
Go and look it up. Or space-time diagram does it, actually. That tells you. And that gives you really the insights into what can cause things because the information can get to you and what can't because the information can't get to you.
Okay. Fascinating. All right. There you go, Matt. Thanks for such an easy question too. Now, let's move on to a text question from Miranda. Is there an assumption that an Earth-like planet or habitable water world would require a moon to help create tides like we have on Earth to enable life in the ocean? Or does it not matter if a planet has tides to have life? In other words, does a planet need a moon to have life, particularly in its oceans?
Yeah, a great question, Miranda, and one that's certainly thought about long and hard by astrobiologists. So it's not the tides that are the issue here. So you could certainly envisage a planet that doesn't have tides that could form life. We do think, in the case of the Earth, that it was the tides that actually allowed life to migrate from being ocean-dwelling to being on land, because what the tides do is they give you this zone where sometimes it's wet and sometimes it's dry, and it's a kind of intermediate zone between the ocean and the land. So for us on Earth, it may be that we're land dwellers because of the tides, because our very, very distant ancestors crawled out of the sea and had an environment that was kind of benign because it was wet, and it was going to be wet again, a lot wetter soon. The high tide every 12 hours, and so the thinking is that yes, perhaps tides played an important role in the evolution of life from being ocean dwelling to land dwelling. However, there is a bit more to the question than that, because we think that the moon has helped to stabilize the Earth's axis of rotation. I mentioned a little while ago that the Earth's equator is tilted to the ecliptic, the plane of the Earth's orbit, by 23.5 degrees, and that's actually the tilt of the Earth's poles with respect to the plane of its orbit, or perpendicular to the plane of its orbit, if you want the full thing. So the Earth's tilted over at 23.5 degrees. It's what gives us seasons. But the moon is thought to have stabilized that tilt because on the planet Mars, where there are two tiny, tiny moons that have no effect whatsoever on the planet's rotation, Mars has actually changed its tilt over relatively short periods, probably tens to hundreds of thousands of years. Its tilt has moved. And that would be a very bad thing for any evolving species, because you've suddenly got this whole new regime of seasons and not the kind of stability that you need. So a big moon like ours, our moon is 1/80th of the mass of the Earth. It's a quarter of its diameter. It is a substantially large object. That is thought to have acted almost like a flywheel as it revolves around the Earth. And kept our axial tilt stable. So maybe a big moon is something that will be very desirable for the evolution of life, but it might not be essential. We simply don't know, because we've got an example of one ourselves. But it's a great question, and certainly one that's in the minds of astrobiologists.
Yeah, I suppose it is circumstantial. Like if life developed on a planet that didn't have a substantial moon, it would adapt to that environment and perhaps thrive under whatever circumstances. But it might evolve in a very different way, because it, if the tides are the reason we ended up on land, that might not happen there. It's a really interesting conundrum. It is. Thank you, Miranda. And I think that wraps up segment 2. I think it does. Yes, it does. Gosh, I'm losing my place. We've been all over the place today. There's been a lot to talk about. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a small break from the program just for a moment to talk about our sponsor, Curiosity Stream. Now, if you love documentaries, this is the streaming service for you. It covers just about every facet of documentaries that you can think of. And of course, as a Space Nuts listener, I'm sure space is at the top of your list. And I'm just looking through the documentary list now for space and space science specific documentaries on Curiosity Stream. And they're all fascinating. I want to watch the lot. Of course, the moon is the subject of much interest at the moment. So there's a documentary called Destination Moon, which is an original Curiosity Stream production. There's an interesting one. You know how much I love what-if questions. Well, there's a documentary called A World Without NASA, which I haven't really looked into, but I'm intrigued. What would it be like if NASA didn't exist? The Mars Insight mission is the subject of a documentary called 7 Minutes to Touchdown. And Fred and I have talked often about those 7 minutes of terror as objects break through the Martian atmosphere and touch down. Some of them don't make it, of course. There's documentaries about exoplanets and Dragon spacecraft and climate, eclipses. There's just so many. And you can check them all out at curiositystream.com. And you can watch it through multiple devices. So it's very easy. You can log in on your PC, your phone, pad, iPad, tablet, whatever you want to call it. You can also watch it through Xbox and smart TVs and Apple TV and Amazon Fire and Roku. So many options in so many categories. So if you want to take advantage of the offer, there's a special URL and it'll get you 25% off as a Space Nuts listener. So curiositystream.com/spacenuts, and then you use the code word Space Nuts for 25% off an annual plan. curiositystream.com/spacenuts and the code Space Nuts. You can sign up today with our sponsor, CuriosityStream.
Space Nuts.
Rightio, we will continue with our questions, and we are going to the next one. Oh, shock horror! It's about black holes. This is from Stefan.
Hi guys, Stefan here from the north coast of Ireland. Big fan. I've just got like a quick question. It's just as an impossible thought experiment. Nothing can escape from a black hole. Okay, this is what we say. So, what if you had two supermassive black holes passing each other at quite a close distance, but with enough escape velocity that they weren't going to get sucked into each other's gravity? So two supermassive black holes passing each other really fast. And then imagine you had like one small, like maybe one sun-sized black hole in the middle. Would the gravity of the two supermassive black holes not be able to rip apart one small, relatively small black hole and send its contents, like rip apart its contents and send it flying out? If you get what I'm trying to say. I don't know if you want to talk about it or what you think. Thanks, guys. Love you.
I love you too. We don't want to talk about it. Well, okay, we've got three black holes by the sound of it. You've got two supermassive black holes that are sort of passing each other, and the poor little one in the middle, and he's wondering if the power of the two, which would be equal, would counter any impact on the one in the middle. Is that what he's saying?
Yeah, that's right. So
I reckon they'd all rip each other to shreds. That's what I reckon.
Yeah. So, I mean... they're passing so near to each other that they're not going to, or so fast that they're not going to merge. There's even in extreme gravity, there would be a gravitational null point, which is akin to our Lagrange points that we often talk about. Okay. It's the same sort of thing. There's a null point between the Earth and the Sun, and if you put something there, it basically feels no gravity, but it's something that is not particularly stable. You can't put something there and just leave it there because it'll tend to move about. It'll be drifting out, which is why the James Webb Telescope, which is at the second Lagrange point on the other side of the Earth from the Sun, has to have thrusters to keep it on an even keel. So that's all. That's what happens with things that aren't black holes. So, to be honest, I don't know what the answer will be. You've got a gravitational null point, but you've also got, with black holes, they're not, yes, it's a singularity, but it's got all this other baggage that it carries around with it.
Yes.
It's swirling around. And all of that
They're just huge bag ladies, aren't they? That's what they are.
All of that would affect the location of the null point, which may be blurred out completely. And, your poor sun-sized black hole in the middle there almost certainly would move one way or the other and get sucked into one of them or ripped apart. But it's a nice thought experiment.
It is.
And I do quite like thinking about things like that.
Yeah. I love the way people come up with ideas for questions. Like there's been some real pearlers today. It's been great.
They have. That's right. Keeping me going.
Yeah. Well, he didn't get to rehearse them. This is all blind. Okay. We'll move on to no introduction needed.
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres, including science fiction. And today's question is a relatively straightforward one for my current science fiction novel. in which my heroine just destroyed an interstellar spacecraft that was powered by a fusion motor. So she caused a thermonuclear explosion, and the shock wave hit her spacecraft and sent it into a tumble. I'm going to presume that she was far enough away not to get killed by the radiation. So my question is about the tumbling. I have read that there is no dizziness when you tumble in space because your inner ear and what you see are not in conflict. So I wanted to check on this. My research, the one solid thing I found was about the Gemini 8 incident in which Neil Armstrong saved the day. So can't wait for the answer. Berman Gorvine, over and out.
Thank you, Martin. I love his questions. He's always thinking outside the box. My first command as the captain of that spaceship would be to engage inertial dampeners.
Yeah, that's right. That would be it. That would be
the first thing.
Yeah.
But what happens when you tumble in space? Do you not really feel the effect like you would tumbling on Earth, chasing cheese down the hills near Gloucester in the UK, for example?
What on earth brought that on?
Because it happened last week.
Okay.
And a woman won her championship unconscious because she knocked herself out.
Oh, dear me.
Still crossed the line.
Yeah, I didn't see that. I didn't hear about that.
That's tumbling to the nth degree, but tumbling in space.
But not in space, that's right. So, Martin, I don't know the answer to this because it's kind of physiology rather than astrophysics. But I take your point about the disconnect between the gravity vector, because there isn't one, and which your inner ear responds to, and your vision. But my guess is you'd still feel pretty sick.
Yeah,
people experiencing those 0G parabolic flights that are often used to give people an idea what weightlessness is like. The aircraft's called a vomit comet, and that's because even though you're not feeling gravity, your insides are so confused by what's going on that you throw up, and I bet your heroine throws up as well.
Oh, you better write that into the story. Yeah. We want space vomit. We want space vomit.
With an acknowledgement to the chief space vomiters, him and me.
Yeah. I think you'd get tossed around a lot too, wouldn't you? If the thing's tumbling, and you're inside it, you're going to get bounced around. You're going to hit things. Things are going to hit you.
Yeah,
it wouldn't be pretty.
No, it wouldn't. It would not be pretty. That's right.
All right.
Hanging on, I think.
Yeah, indeed. You'd probably have to have magnetic boots or something. Yes, all right. Thank you, Martin. Not sure we helped, but the inertial dampeners, definitely the way to go there. And finally, we have a text question from Robert, who is in Vienna, Austria. And he says, what aspects of our universe determine the speed of light in a vacuum? Are we lucky that the number is almost exactly 300,000 kilometres per second and easy to remember? Or have units been chosen to make this a nice number? And do we have to feel sorry for people in a multiverse where the speed of light is probably something nasty like 215,335 kilometres per second? Love your show. Cheerio, Robert from Vienna.
Where I was a few months ago. Yeah, it was a lovely city. In fact, my colleagues with whom I spent time in Vienna in February at the COPROS Science and Technical Subcommittee, they're there at the moment on the main Committee on the Peaceful Uses of Outer Space. So it's a nice reminder to have, the thinking about the lovely surroundings in Vienna. Okay, and while we've been talking, I've just brought up the speed of light in kilometers per second, 299,792.458 kilometers per second. So it's not really a round number.
No.
And it's comfortably close to 300,000, but it certainly wasn't chosen to be that, because the meter is defined in terms of the circumference of the Earth. That's how you work out what a meter is. You take the planet and you divide it up into, well, it will be 40,000, I think, for kilometers. Is that right? Anyway, it comes from a completely different sort of fundamental quantity, if I can put it that way. And it just turns out...
Actually, Fred, can I interrupt?
Yeah,
I need you to go back, because I dropped out, and start from, it certainly wasn't chosen, as in the 300. Yeah, because I had a dropout. I thought we were going to get through it today, but we didn't.
I didn't notice it.
Yeah, I did.
It certainly wasn't chosen to be 300,000 exactly, because this is determined in terms of kilometers and meters, which were themselves originated as a fraction of the circumference of the Earth. So that, they themselves come from a completely different physical quantity. You take the Earth and divide it up into small enough chunks, and you've got a unit of length, and that becomes a standard meter, which I think is in Paris still. So, so it's not chosen to be a round number. In fact, I grew up thinking it was 186,000 miles per second. That was the number that was ingrained in my mind until quite late in my life, because we worked in miles. So it's the speed of light's measured by very accurate means these days. It was first measured back in the 1600s by a Danish astronomer whose name was Dr. Rømer. He looked at the moons of Jupiter and said, they're doing some funny stuff here. And he figured out that was because he was not allowing for the travel time of the light from one side of the Jupiter orbit to the other for these moons. Very clever stuff. Yeah. He made the first measurement, which actually wasn't too bad. So, yes. So, nice question, Robert. And
it is what it is. And I suppose another culture in another universe or another part of this universe would have their own way of measuring things, and their number would be whatever the number is.
Exactly.
And it would be the same speed.
Yep. There is one nice aspect of the speed of light, though, and it kind of mixes up the kilometers and imperial units. In 1 billionth of a second, light travels 1 foot.
Oh, there you go. Yeah. It's an exact.
That's because it's 30 centimeters roughly is a foot.
Yeah.
So that's how it all works. In a billionth of a second, light travels 1 foot.
All right. Very good. So, yeah, not very helpful, but very good.
Sometimes useful.
Yes, maybe. All right. Thank you, Robert. Really appreciate it. Thanks for all the questions that came in today. We've really enjoyed ourselves. There's a bit of homework to do. I'm sure Fred's written down notes so we can chase them up for next week. But great to get your questions. And please keep them coming in. You can send them to us via our website, spacenutspodcast.com or spacenuts.io. And you can send us text or audio questions through the AMA tab or through the button on the right-hand side of the home screen that says send us your audio question or comment or whatever it says. I can't remember. And one more thing, if you're a social media user, particularly on LinkedIn.com, we're on there as well, and we need a minimum of 150 followers so that we can do our recordings live to LinkedIn. We already go live via YouTube and through Patreon and through Facebook, but we want to add LinkedIn, but we need to get to 150 users. So if you're a LinkedIn user, just use their search engine and look for Bitesz.com, Bitesz.com. That's the easiest way. The other way is link.com/company/Bitesz, I think. Yeah, something like that. But just do Bitesz.com in your search engine for LinkedIn and follow us there. And when we get to 150, we'll be able to offer live studio recordings as we record them, is what I'm trying to say, which we tried to do today, except for the internet dropouts. Still haven't solved that one. Fred, thank you as always. You are fantastic. We really appreciate it.
It's very kind of you to say so, Andrew. Wish I knew more answers than I do, but never mind. That's all right.
Well, if we knew all the answers, we wouldn't have to be here.
Oh, we wouldn't. That's right.
Exactly. All right. Thanks, Fred. We'll catch you next time.
Yes, looking forward to it.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio because. And from me, Andrew Dunkley, thanks for listening, thanks for watching, and we'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.